Welcome everybody to the recorded lecture. So we'll be talking today about various kinds of radioactive decay in more detail. And I wanted to start with something I talked about last time, which was the decay of excited states of calcium. So we had calcium over here, 47. This was the configuration of the nucleons, the protons, and the neutrons. And they had all these various gamma decays. And we were trying to understand why we don't see a decay from these 1/2 plus to 3/2 plus states to the 7/2 minus. And we'll talk about that today, try to figure out why that is. We might cover it in more detail a bit later as well. So this is the ground state. You see there's one unhappy neutron in the F7/2 state. That's right here. You remember the parities correspond to the various orbital angular momentum letters. So we had, S, P, D, F, and I can never remember the parities, so I just like to write them down so I can remember what's going on. So, okay, those were the parities corresponding to the various orbital angular momenta. So why don't we see a 3/2 plus to a 7/2 minus transition? Well, we can think about what actually happens. So what actually happens is you have an initial calcium that's excited, we put little red lines showing it's in some excited state, and then it transitions down to a less excited state and emits a photon in some direction. Now, the thing is, the photon actually takes away some angular momentum with it. And a photon is a boson, meaning it's got angular momentum quantum numbers that are integers, whole integers, not half integers. And of course, there's conservation of angular momentum. So we know that if this guy was in some initial angular momentum state Ji, then that has to be equal to the angular momentum of the final state plus the angular momentum of the photon, which I'm going to call L. That's sort of common notation, but I'm going to put a little gamma subscript to remind us it's the photon that has that angular momentum. And as it turns out, because photons moving at the speed of light and they have a polarization, quantum mechanically, they actually are not allowed to have zero angular momentum. They always have an angular momentum quantum number that's at least 1. So it's got one of these for its angular momentum quantum number. So what do we have here? We have a kind of selection rule in the sense that we know from addition of angular momentum that the quantum numbers J, I, and JF, they have to satisfy the following, right? That if we take the absolute value of the difference between the final and initial quantum numbers, that has to be less than or equal to L gamma, which is less than or equal to, oops, should be a gamma here. Is less than or equal to the sum. Okay, so that's the rule that has to be satisfied. So if we look at this 3/2 and 7/2 transition, we'll have 7/2 minus 3/2, so that's 2, less than or equal to L gamma less than or equal to 3 halves plus 7 halves, which is 5. So for this transition to happen, the photon has to carry away quite a bit of angular momentum, right? Well, at least 2 units, 2 h-bar units of amount of angular momentum. And so we can wonder if that's something that is physically reasonable, or is that a kind of process that can occur with high probability or not? Obviously, it can occur because we have this 3 half minus state that decays to the 7 half minus state. And remember what that is. That is the kind of first excited state. It's where this neutron hops up here to the 3 halves, right? And then falls back down. Well, that's the excited state, the 3 half minus. Remember, P is minus. And it falls back down and emits a photon. That's 2 MeV. The other one, the, say, 3 half plus, that's where you have this 3 halves guy, which is in the d orbital, which is plus parity, hop up here, over here. And apparently when it gets excited over there, it doesn't want to hop back down. It sort of doesn't want to go back to the ground state this way. This doesn't happen. And we might wonder why. So that would be this 3 half plus to 7 half minus. So first of all, it apparently flips the parity, this kind of transition, and that's, for whatever reason, forbidden, or at least very slow. It happens at a very low rate. So let's just see why. It actually has to do with the photon radiation. So when the photon comes out here, like that, it can be of 2 different kinds. So there's 2 kinds of radiation. There's electric and magnetic radiation. And these are labeled with E for the photon and M for the magnetic. And then you typically list the L number of the photon. So you put L gamma and L gamma. So there's, E1 radiation, E2 radiation, 3, and so on. And similarly, there's M1, M2, M3. And these guys also have their own parity, right? So we know that this one is and they're opposite, as it turns out. So this one is odd parity. This is even and odd, but the magnetic ones are opposite. The L is equal to 1 actually turns out to be even parity, and this one turns out to be odd, and this one turns out to be even. The parity, remember, call it with a pi. And why is that? Well, we can look at sort of dipolar radiation, which means in the electric case, you can think of it as oscillating charges. So you have a dipole, an electric dipole. And if this dipole is sort of oscillating, it'll generate some radiation. And that corresponds to this E1 case. This is also called dipolar radiation. So it's electric dipole radiation. We can see that it's odd parity because if we reflect the coordinates, then this plus charge and this minus charge, they get exchanged. And so the direction of the electric field will point in the opposite direction. So everything will pick up a minus sign. On the other hand, magnetic dipole radiation is a little bit different. That you can think of as an oscillating or a kind of a charge that's orbiting around. So if you have a charge that's making an orbit around, that'll create a little magnetic moment. And magnetic dipole radiation corresponds to radiation coming from a oscillating magnetic dipole. But a magnetic dipole, it's proportional to the charge times the location of the charge, which is r, crossed with the velocity vector of the charge. So let me draw it a little better here. You have a kind of orbiting charge in a circle, and it's got some location, and it's moving sort of uniform circular motion here, v. And so when you do a parity transformation, you reverse all the coordinates. What'll happen is both the, so we'll put a pi here for parity, both the r vector and the v vector pick up a minus sign. So this becomes just the same thing. So you can see sort of because of the nature of the magnetic dipole, it won't pick up a minus sign for a dipole radiation. And then you can show that it sort of alternates for the even and odd values of L gamma, the photon quantum number. So what does that mean? That means since parity is conserved, right? If you have a photon leaving with odd parity, then there must be a parity change between the initial and final states. So we can draw a little table sort of representing what happens if you have different kinds of radiation, say E1 versus M1 or E2 versus M2. And you can ask, is there a parity change? For that kind of radiation? And the answer is yes for this one, right? For E1 because that's odd parity, and it's no for this one because that is even parity. And this one is even now, but the M2 is odd parity again, so that one corresponds to a change in parity between the initial and final states. So that's the idea. And the other thing is, and this is what we might cover later, you can actually calculate the probability that one of these gamma ray photons is emitted for a particular transition for a certain energy. And you get these kinds of curves here. So this is the half-life of the transition. Remember, it's related to the inverse of the rate. So the smaller the half-life, the faster the rate. So you can see the fastest transitions, the ones that occur, are of course the E1, M1, because they don't correspond to a lot of angular momentum being carried away. It's generally the case that photons do not want to carry away a lot of angular momentum because that corresponds to a kind of complicated radiation that's difficult to generate in terms of the probability of that happening. The most likely things to happen is that you carry away just a little bit of angular momentum. So, and we can see that the electric dipole radiation is a little bit more favored over the magnetic. And you can actually calculate all this. It's a relatively complicated sort of electricity and magnetism type problem, but we might consider it later. So what do we have here? Let's see. So we can look at this one. This is 3/2 to 7/2, right? And so we know that for that case, the angular momentum of the photon is at least 2. somewhere between 2 and 5. Now we know that, of course, the large numbers are not favored, so it's probably going to be the lowest possible is 2. And we can look here, there's two kinds of transitions here, E2 and M2, and the E2 one is much more likely to happen than the M2. I know it might seem that way because of the lines are close to each other, but this is actually a logarithmic scale. So you see this is 1 second, and this is already, you know, sub 1 second, and this could be multiple seconds. So it could be quite a bit larger in terms of the rates. And so we know if we look at this E2 versus M2, E2 corresponds to no parity change. So that should be favored. That means this transition, 3 half minus to 7 half minus, is likely corresponding to an E2 photon, right? And M2 is less likely, so that's why we probably will not see something like a 3 half plus to a 7 half minus, because that would require, you know, at least angular momentum 2 and a parity change, which would mean it could either be sort of like an M2 or maybe a E3, right? It can't be E1 or M1 because we know that it's bounded by 2. So that gives us a little bit of a hint on why we don't see that kind of transition. 1/2 to 7 halves is even worse because that one, it's the minimum angular momentum is 7 half minus 1/2, right, which is 3. So the transition here between 1/2 plus to 7 half minus has to be like an E3 transition, which is just not very likely. You can see that the estimated half-life for something like that is, you know, up here at 10 to the 8. And of course, it depends on the energy of the transition. The higher the energy is, the more likely it is to happen, because the very high excited states, of course, decay faster. But nevertheless, it's going to be more difficult for that kind of transition to occur. So sometimes this large angular momentum transfer leads to very large half-lives for transitions that are otherwise very high energy, have very large gaps. So this kind of thing, transition from here to here, likely doesn't happen because of something like that. So that's what I wanted to mention. But for most of the class, I wanted to discuss not gamma radiation, which I think will lead us too far into the weeds of, you know, electro dynamics and so forth. Oh, by the way, I wanted to show you a picture of dipole radiation just so you see what it looks like. This is electric dipole radiation. So, of course, electromagnetic waves have both electric and magnetic field components. The distinction between electric and magnetic radiation is just that which one has the radial component. So if the electric field is radial, meaning it points out radially like this, you see the little arrows, it's the electric field. It's pointing out. So that's electric dipole radiation. And that means the magnetic field is perpendicular. So it's sort of on the surface of concentric shells. And it's not pointing out radially. So this is electric dipole radiation. And on the other hand, you can have magnetic dipole radiation, which would be the magnetic field pointing out like this radially. So that's the only distinction. But it's good to know that, you know, when you see this kind of notation, that it doesn't mean that, you know, M means purely magnetic. That doesn't exist, because any radiation will be a combination of perpendicular electric and magnetic fields. It just, the distinction is which one is actually in the radial direction, which one is pointed outwards. So that's the difference. And we can discuss this more, but it's a little bit complicated in terms of the physics involved. So what I wanted to talk about today is kind of cover two sections that in the book that we sort of one we kind of neglected, which was section 2.2 in Lilly, which was about fission. And then I want to also cover alpha decay, which is interesting. So I want to skip to 3.4 afterwards. So we will cover chapter 3 in bits and pieces. So some of chapter 3 includes, this kind of stuff with the electric and magnetic radiation, but I want to hold off on that for a bit and talk about alpha decay. But let's do fission first. So fission is when you have very large nuclei and they spontaneously break up into pieces. So as it turns out, so there's this cartoon, it's a big nucleus. You have this mushroom guy trying to shove a proton into there, and it causes an explosion. So that's spontaneous fission. And it can actually be understood through the liquid droplet model. So what happens is that you have a very large nucleus, right? And it becomes unstable to a particular kind of deformation that kind of splits it. So it becomes energetically favorable for it to start kind of pinching off. And forming a kind of narrow neck, which is a little bit tricky to draw. And eventually splitting into halves like this. And so this becomes energetically favorable. And the relevant terms that are kind of contributing to kind of penalize this kind of deformation and favor it, it's a trade-off between the sort of Coulomb and the surface area terms in the semi-empirical formula that we had. So it's a trade-off, and we can think about what that trade-off looks like, and we can actually calculate what's going on. So what's observed is that basically the half-life for spontaneous fission, it gets really small with this quantity, z squared over a. So the more z's you have, the more protons compared to the total mass number here, the more likely it is to sort of split. And we can actually calculate why you have this dependence, why it depends on z squared over a by using the liquid droplet model. So that's pretty cool. So let's try to do that. The idea is you want to figure out, so the liquid droplet model assumes sort of a sphere, right? You have a sphere, it's got some radius, right? And a deformation of it would correspond to some kind of, you can think of it as an angular dependence for the radius. You can imagine that well, assuming some, say, rotational symmetry around the z-axis, say, you can imagine some kind of deformation that retains a sort of azimuthal symmetry, but deforms the sphere, say, by sort of turning it into a dumbbell shape like this, like that. And that could be a kind of deformation that depends on theta, meaning the usual polar coordinate between the z-axis and that radial direction there. So, okay, what would that look like? Well, we could do a multipole expansion just like we do for the radiation and so on. And vibrations, it's again an expansion in spherical harmonics. So just to remind you, or maybe tell you, I guess, the spherical harmonics are, and I'll mention in more detail what they actually look like. So they have a sort of constant factor out front. These are factorials. So you have a square root thing out front. And then you also have a Legendre polynomial. And so we see the only phi dependence, the sort of azimuthal direction, the one that goes around here that remains symmetric, is in this M number, right? And that's the only place where phi appears, the sort of polar coordinate that goes around. So for symmetric things like that, we actually have just M is equal to 0. And if we put M is equal to 0, we get YL 0. It only depends on theta now. And it's sort of more simple here. It's 2L plus 1 over 4 pi. And then it only depends on, you drop the 0 up here because this just becomes the Legendre polynomial PL cos theta, like that. So the spherical harmonics become just proportional to these Legendre polynomials. And they have a certain form. You can sort of look them up and see what they are. But we can use this to start expanding our shape. And again, the idea is that if you're looking for deviations from a sphere, then the lowest order kind of deformations that cost the least amount of energy will be sort of the lowest order Legendre polynomials. So we can start thinking about, expanding this thing. So you have R0, right? You have 1 plus, alpha 0 P0 cosine theta plus alpha 1 E1 cosine theta. So these are like expanding into these modes, right? And these alphas are just some coefficients. And so on. And so we kind of know, so this is like the L is equal to 1 mode. And we know for that one that corresponds to translations of the whole shape. So that corresponds to just taking our sphere and translating it up or down. This is just quite similar to the discussion we had last time about vibrations. So this term is kind of not contributing to the shape deformation because it just corresponds to moving the droplet. So it shouldn't contribute anything to the energy associated with deforming the droplet. So then you have this guy, and this guy is just a constant. It doesn't depend on theta at all. And that corresponds to, of course, changing the overall shape. Or not the shape, you're changing the overall radius, right? It's like expanding or contracting the the droplet. So that one might contribute. That definitely is going to cost some energy. And then you have this guy, which is sort of the leading order mode of the deformation that could cost some energy. So the next thing we have to do is to make sure that we conserve volume. So we know that the nucleus is largely incompressible. So that means if it deforms, if it goes from this kind of shape to some other kind of shape like this, it has to conserve volume. Meaning that, the volume of this guy, which we know is sort of 4/3 pi r0 cubed, that has to be conserved so that the volume of this guy is also 4/3 pi r cubed. And as it turns out, you can show using this as sort of your deformed shape that constrains the value of this constant. So you can work it out. It is a little bit complicated, so I'm not going to do that, but the conserved volume constraint tells us that this R has the following form rather. It's 1 minus, now I'm going to assume, I'm going to assume that the deformation is small, so I'm going to call this epsilon, meaning some small amount of deformation. And in that case, we have that the volume constraint gives us 1 minus epsilon squared over 5 to leading order in epsilon plus epsilon p2 cos theta. So the volume of the shape described by this particular R for all the different values of epsilon, it should be just equal to the original volume, this one. Let's see what it looks like. So you can fire up Mathematica here, show you what's going on. So here we're going to do a spherical plot, and I forgot to put in the volume conserving term, but here we go. See here, epsilon squared over 5. And let's see what happens. So this is the radius of, it's the radial coordinate, and it depends on just this angle theta. And this is the azimuthal angle. It goes around from 0 to 2 pi. It's symmetric around here. So you get this kind of surface. And let's let epsilon vary from 0 to 2, although we know that we sort of don't really expect this to only work well for small epsilon. So when epsilon is 0, you got your sphere right here, and let's see what happens as you sort of increase. This is sort of the lowest mode of deformation that would play a role in the energy. See what happens here. So it kind of gets skinnier, so it becomes more ellipsoidal. And as you start cranking it up, see, it'll start to develop a little valley here. And then start to pinch. And you get up. I think I went too far. So starting to do something bad here. Epsilon should never get this big. I have it at 1.67 or something. So, but you see it'll pinch off, basically. So that kind of mode corresponds to sort of the lowest mode description of what happens in spontaneous fission. The idea is that the energy, it becomes favorable for the energy to develop a non-zero epsilon, meaning it's no longer just happy sitting as a sphere. It actually will be able to go to a more energetically favorable state by deforming in this way and starting the pinch off process. So that's what we kind of want to understand with the semi-empirical mass formula. So let's try to do that. So what do we know? We know we have the semi-empirical mass formula, right? Which tells us about the binding energy. And well, you can recall what that is. We've got the volume term, right? We've got the surface area term. And we've got the Coulomb term. And then we have the quantum mechanical terms, which are not going to be important for our discussion because the spontaneous fission is really a competition between this term and this term. So remember, we want binding energy to be big, right? Because that's favorable. And the surface area term, if the surface area gets bigger, that's a problem because this comes in with a minus sign. So more surface area means less stable. So you would think that this would never work because it's got a larger surface area. But this also has a smaller Coulomb energy, meaning this term, the magnitude of this term gets smaller, so it gets less negative. And it's then a competition between the surface area and the Coulomb energy. If the Coulomb part sort of wins out, then it's actually possible that this kind of deformation will be energetically favorable. So how do you work that out? Well, you have to know what happens to both the Coulomb energy and the surface area when you have this deformed shape. So you have to take this and actually calculate what the surface area is. And that's, not necessarily completely trivial, but you can show that the surface area corresponding to this shape is equal to, well, there's the leading order term, which is, of course, the surface area of a sphere. But it gets a correction. It gets bigger with epsilon, and the amount it gets bigger is 2/5 epsilon squared plus higher order terms. If you want to know how this is done, well, lots of ways to do it, but I thought of sort of doing it this way. You can put the z-axis along this direction, and then we know that the shape looks something like this, right? Sort of dumbbell shape. And we know that the polar angle is sort of like this. All right. Oops, I didn't want to use that pen there. Let's see. Get another color, perhaps. Go. All right. The polar angle is sort of right here, right? And then you have this distance right here. And this distance is, and we know that this guy right here, that's just r theta. And so this distance right here is r theta sine theta, right? Opposite over hypotenuse there, you got a little right triangle. So we can think of this as a solid of revolution, right? You can imagine rotating this around here, around the z-axis. You can rotate this little bar, and that'll give us a circumference of 2 pi r theta sine theta, right? So we rotate that around, and then we have to get the surface area. You also have to multiply by sort of the arc length along this red curve. We call this ds. So the surface area, let me kind of make a little more room here. Let's see here. Move over a bit. Okay. So the surface area is equal to 2 pi, and it's the integral of r theta sine theta. That gives us the circumference of the circle, and that gives us, and we need the circumference of the circle times this little ds. That gives us a little surface area element, right? It gives us a little ring, basically, that sort of looks like that. Sort of hard to draw, but it's a little ring with a width ds and a radius r theta sine theta. And then we just have to add up the rings, right? So we integrate, we get a volume of the surface of revolution. Now the ds is a little bit tricky. You can think of this as a sort of parametric surface. So you have, maybe this is the y coordinate, so you can think of the y and z coordinates, right? The y coordinate is just what we have here. It's the r theta sine theta, and the z coordinate is just the cosine, right? It's r theta cosine theta. So this is like a parametric curve, if you want to think of it that way. And so actually it turns out that the line element, this is some calc that maybe you don't necessarily remember, but it's just, you take the derivative of the, and you can think of this as y as a function of theta and z as a function of theta. Then this just becomes dy d theta squared plus dz d theta squared, and this is d theta. And that's what you have to plug in for ds. Plug it into here, and you get something complicated. But let's try to work it out. I'm actually going to try to work it out in Mathematica, which is sort of my favorite thing here. So here is our r. So the surface area should be an integral of r, right, times sine of theta. And then we have this complicated ds, but it's just a derivative. Actually, let's work out that. So y of theta, right, y of theta is just r times sine of theta, and z of theta is the same thing, but cosine. And then we can look at, we need to take the derivative of this guy with respect to theta. We square the whole thing, and to that we add the derivative of the other one with respect to theta, and we can sort of simplify that, see what happens. So okay, I got some complicated thing, and that has to do with just expanding these Legendre polynomials. But whatever it is, and it's this guy, it's dy d theta squared plus dz d theta squared, and we know we have to stick all of this inside a square root. So let's do that. And then that's it. We then integrate theta from, oh, we forgot the 2 pi from the circumference part. So it's 2 pi. And theta goes from 0 to pi. Now, of course, it won't be able to do this. It'll be unhappy because of this complicated square root with stuff. So I'm actually going to interrupt this. And what we're going to do now is look at the leading order in epsilon. So we're going to do a Taylor series around small epsilon, let's say. Let's look at what happens just to order epsilon squared. Still looks complicated, but when we integrate this guy, we got it. This is a little trick too. So when you do the series, it tells you what the next leading term is of order epsilon cubed, but we don't care about that. We just want it to order epsilon squared. So then you take this expression and you can integrate 0 to pi here. And there you have it. Look at this. You have first term, right? 4 pi. We just have it. Do both the terms. So you have 4 pi, which is what we would expect for surface area of the sphere, plus this correction, 8 pi epsilon squared over 5, which is just, if we divide by 4 pi, right? So we can take all this, right? And divide by 4 pi, we get the leading order of 2/5. So kind of complicated, right? But it can be done. And indeed, you find that the leading order correction is 2/5. That's the increase in the surface area due to this funny shape. So, okay, that's the surface area part. So we figured that part out. It's already kind of complicated. So you get a change here, right? You get a change here of delta B of minus 2/5 epsilon squared, right? That's the change in the surface area. And then that must be what contributes to this term. Makes it more negative, so less stable. Okay, but what about the Coulomb term? Well, the Coulomb term is harder. I'm not going to do that one, but I'll likely assign it in the future as an extra credit. It's hard to do because you actually have to calculate the Coulomb energy. So the Coulomb energy is 1 over 4 pi epsilon 0. And then for like an arbitrary charge distribution, you have to compute this integral. Do 1/2, and it's the integral over two 3D coordinates of the product of the charge densities divided by the separation between those two coordinates. So it's just the Coulomb potential there. This is like the charge, right, at one point times the charge at another point, and you divide by the distance between those two charges, and then you have to integrate over all pairs of charges. That's what these two integrals are, and you divide by 2 because you only care about pairs of charges. You don't want to double count. So you can actually do this, and I mean, it's hard, right? Because what is your density? Well, your density is, it's a uniform density. And we know lambda is basically the total charge divided by the volume, which, remember, we maintained fixed to the original volume. So it's a uniform charge density, and then this is step function. And you've got here our theta minus little r, the radial coordinate. It just says that your density looks like, right, this is z, just looks like it's a uniform inside the sort of dumbbell shape, right? Some uniform lambda and 0 outside. That's what the step function does. Then you have to do that, and it's a little bit tricky. Tough integration. But what do you find? You find in the end that the contribution scales like, or not scales like, but the actual contribution that you get, it decreases the Coulomb energy. So that means it increases the binding because it's minus Coulomb. So the Coulomb gets more negative, this part, which means that B gets more positive, right? So the term that you actually get, the change in B is, turns out it's 1/5. And I actually haven't been able to calculate this 1/5. It actually is really challenging to get this. In the book, it says something like it can be shown that it's 1/5, but it's actually very hard to show that. At least using this kind of brute force way with integrating these charge densities. Incidentally, it's hard to show that with this formula, it's hard to show just the energy of a sphere. In the homework, I just told you that the energy of a sphere of charge is like 3/5, q squared over 4 pi epsilon naught r, but that's actually kind of hard to show with this formula as well. You have to, there's a trick to make it easy, but yeah. So there you go, you get 1/5. So binding energy goes down due to the surface area, but it goes up with the Coulomb. And so it's when these things balance that you get, it becomes favorable, right? So, and both are proportional to epsilon squared, right? And that's important because it means that as soon as this term, this delta B is positive, then the system will want to just increase epsilon squared to just keep increasing B. So there's like a critical, there's a critical value, which is when so there's a critical condition for when spontaneous fission should just happen automatically. And the critical condition is that you want the Coulomb term to be bigger than the surface area term. And what is that condition? Well, you got some cancellations. Of course, this epsilon squares cancels, the 5 cancels. You can take this A to 2/3 and divide, and then this just becomes A. And so you get the Z squared over A, which is really nice because that is the combination that we were hoping to get. That when that is bigger than 2AS over AC, you get spontaneous fission, because then epsilon, it just becomes favorable for the shape to deform like that, just as the binding energy continues increasing with the epsilon. And again, just to remind you what that looks like, right? It starts deforming like this, right? It goes whoop and starts pinching off like a droplet, spontaneously pinching apart. That becomes favorable when Z squared over A is bigger than 2 times the ratio of these, the surface area and Coulomb semi-empirical formula combination. And this, you can substitute in numbers, is around 50. And now let's go back and see what 50 is over here. Well, we look here, 50 is where you really, it's over here. It's where this half-life would be very, very small. And that makes sense because at 50 is where this process should be instantaneous. And so what happens over here, where your Z squared over A is smaller, is just that there's a barrier to forming the two droplets. It could very well be that the two droplets are energetically favored. So if this is the energy, and maybe this is a function of the deformation parameter epsilon, it could very well be that, so this is the energy So maybe here is 0. And here it's, like 2, where it's completely separated. So it looks like this over here, completely separated here. The nucleus is just a sphere. It just could be that the energy, it's stable here. This funny marker. Hold on a second. Let's see. Could be that the energy is stable here, and then there's just a hump like this. And then it's more favorable, separated out. Could be like that. So that's what you would get for values of, that's what you would get when z squared over a is sort of less than, but similar to 50 when you're kind of over here. There's just a barrier, right? It doesn't want to go through all these intermediate states. It just costs more energy. It's basically, it'll cost some energy to be in these, to start the process. But still, through fluctuations and things like that, it can happen. So there'll be some rate at which the transition happens, and that rate will, generally depend on the size of this barrier. And that's what we're seeing here, is that even though it wouldn't necessarily happen just instantaneously, that's what happens at 50. For these intermediate values, there's likely like an energy barrier for that to happen. And so that's why the half-life is longer, because you have to wait for it to just sort of fluctuate and overcome this energy barrier. All right, so hopefully that makes sense for spontaneous fission. So again, for the case where z squared over a is sort of bigger than equal to 50, basically you just get it just instantaneously starts deforming that way. But we can understand, a lot of what's going on here by thinking about this semi-empirical formula and the competition between various terms. And again, I want to emphasize the importance of this multipole expansion, right? It's again always the case, since we're working so often with spherical objects. If you want to know sort of what's the leading order perturbation to the shape, either due to vibrations or the liquid droplet thing, deformations, you do a multipole expansion, which means an expansion in spherical harmonics. And then if you have azimuthal symmetry, if you're assuming sort of rotational symmetry around the z-axis, like in this case, then the expansion is naturally in terms of these Legendre polynomials. So it's the theme that comes up over and over again for various things, including fission and gamma radiation, where essentially we're expanding the gamma radiation in order by order in the angular momentum, and that's mathematically the same as expanding in spherical harmonics for different values of L. So hopefully see this sort of math appear over and over again, but in very different contexts. This was really just the property of a large nucleus, sort of collective property of many nucleons. And then up here, we were really talking about filling up energy shells and transitions having to do with single neutrons going into excited states. That's like a single particle picture. Okay, so that's spontaneous fission. And the other thing I wanted to talk about was alpha decay. So alpha decay is quite interesting because it also is, in some sense, you can treat it semi-classically, kind of like the liquid droplet model in a way, but we'll see it's different. It's still sort of single particle ideas will come up. So alpha decay is very interesting. Here is the Q value for various alpha decays and the corresponding half-life. So first thing to notice is apparently the half-life decreases very quickly with the Q value. If you look here, you go alpha decays between Q values between 5 and 6, the half-life goes down by many, many orders of magnitude. You go from like, or here, like you go from 1 second at 7 MeV to like, 10 to the 10 seconds for 5 MeV, just over for 2 MeVs of difference. It's quite amazing change, right? This is, a log scale with many, many decades here. It's a huge variation in the half-life with tiny variations in the decay energy. And just to remind you what the Q alpha is, so how does alpha decay work? You have a parent nucleus, right? And it decays to a daughter nucleus and spits out an alpha particle, which is the helium-4 nucleus. And the Q value, Q alpha, is just it's the kinetic energy of the alpha particle. So it's it's the mass of the parent minus the mass of the daughter minus the mass of the alpha, c squared, and we know that that's equal to the kinetic energy of the daughter plus the kinetic energy of the alpha, assuming the parent's at rest, which we argued, using momentum conservation. The daughter absorbs most of the recoil from the alpha particle being emitted, so most of the kinetic energy is in the alpha. So Q is a measure of the kinetic energy of the alpha. Now let's think about this. If this is the kinetic energy of the alpha, it means we're getting kinetic energies sort of like at 5 or 6 MeVs, seems like a common alpha particle energy. Does it make any sense? Well, if we think about what actually is going on, we'll realize that it doesn't make quite a lot of sense, because what's going on inside the parent nucleus, right? In the parent nucleus, you've got like a ton of protons. Alpha decays occur for like Z, around 90, right? And so what happens in alpha decay? Apparently, an alpha particle pops up in here and gets shot out. Now we know the alpha particle has a charge, Q alpha, of 2 times the elementary charge. And the nucleus, has the charge of the nucleus is, Z or Z minus 2, but it's basically, it would be 90, so Z minus 2 E, which, for us, let's just say it's like 90 E, like a typical value there. We know that there's a Coulomb interaction. The Coulomb interaction is what? Well, it's got to be the product of the charges over 4 pi epsilon naught times the separation. Well, the separation, let's just say it's created in the nucleus. So why not just say it's sort of, maybe they're right next to each other or something. This is sort of, probably this is even inside the nucleus or something. Well, let's just say it pops out like right next to the nucleus, right? We know that the radii here of the nucleus, right, and this is the radius of the alpha. We know that the radius of the alpha, remember, you have this formula, the 1.2 femtometers, and then it's the mass number to the 1/4, or to the 1/3. So it's 4 to the 1/3. And R of the nucleus is, 1.2 femtometers times whatever the A value is to the 1/3. So we can sort of figure out what that is. Let's look at some value. Let's just assume we're looking at here I don't know, like 234. We'll see that. So maybe we're looking at, for instance, uranium 238, right? So after the alpha particle just pops up, it'll have an A of 234, and then so we can plug that into here. And then the separation, right, will just be just the sum of those, right? They're going to be R alpha plus R nucleus apart, and we can plug in these numbers here, and what do we get? So we can, again, sort of fire up whatever calculator you wish. So let's look at this one. So it's 1.2 times 4 to the 1/3 plus 234 to the 1/3 times 1.2. 9.3, okay. So 9.3 femtometers apart. And what is that? What is that energy of the Coulomb interaction? So let's put it over here, just to remind us what it is. The Coulomb interaction apparently is, so Qn, right? That's the charge of the nucleus, this is in 90. And we have times 2 times E squared, elementary charge squared, all over, parentheses there, all over 4 pi epsilon naught and 9.3 femtometers. And that, I like using Google for this, although you have to kind of usually remember what epsilon naught is, because Google doesn't know that. But Google is pretty good at units. I'd avoid things like chat GTP and so on, because some danger it'll do it wrong. But this is just a calculator. So here I put 2 times 90 times the elementary charge squared divided by 4 pi. This is the epsilon naught, the vacuum permittivity. It's 8.85 times 10 to the minus 12th farads per meter. Then I've got my 9.3 femtometers, and you get, 28 MeVs. Huge. Really surprisingly huge. And that's crazy because, what gives? How do we get 5 MeVs if the Coulomb interaction alone is going to be at a scale of like 30 MeVs? You'd expect much higher energy for the alpha particle if it was just to appear there. And so this is where sort of quantum mechanics comes to the rescue. Or alternatively, the way to think about it is if the alpha particle just appeared in the nucleus, it'll never be able to leave, because as soon as it tries to leave, right, it'll see this huge barrier, the Coulomb barrier, that will prevent it from leaving. It just won't have enough energy to overcome it. Because, so how do we think about this? Let's just imagine what the what does the alpha particle see? Alpha particle sees this potential. So if it's created in the nucleus, right, and this is the distance away from the nucleus, and maybe this is the radius of the nucleus, right, roughly. What does it see here? Well, we know that outside the nucleus, there's this Coulomb potential, right? This is, it looks like, 2z e squared over 4 pi epsilon 0 little r, the distance between the nucleus and the alpha particle. And we know around here, it's something like 28-ish MeV. Huge barrier. Now, of course, inside the nucleus, you have the strong nuclear force. So this thing will drop. Maybe I'll draw a thicker kind of thing. So you got this 1/r long range Coulomb thing. And then this thing will drop to some baseline, which, let's see here. So it was sort of worked out. You can kind of work out what it should be. It should go to some low value here inside the nucleus. And there it's minus U, negative, and that's from the strong nuclear force. It's the thing that binds sort of the nucleons together. I think we can, the book has an estimate of what it is. Let's see here. Yes, so you can, so scattering results give that U is about 120 MeV. Really big, right? So what happens? So we know that the alpha particle comes out with like Q alpha kinetic energy. So that's what its energy is far away from the nucleus. We see it, zooming out away from the nucleus with energy Q alpha. That's the energy that it has far away. And of course, energy is conserved, so that must be the total energy it has kind of throughout. So if we draw a line out here and say this is, our Q alpha, this is what should happen, right? If the particle is created with energy, if the particle has energy Q alpha, it could be created in here, right, with energy Q alpha, which consists of basically Q alpha kinetic energy, right? And then it'll have a large negative potential energy, which is this U alpha. That's because that's from the attractive forces of the other nucleons there. And so what should happen? Well, it should rattle around in here with this kinetic energy Q alpha, right? And it can never get over this barrier classically because it's just too much potential energy. It's you would have to have over 28 MeV of kinetic energy to make it over this barrier. And so that doesn't happen normally. But quantum mechanics comes to the rescue because there is such a thing as quantum mechanical tunneling. Particles are actually able to go over potential barriers that have more energy than sort of the amount of kinetic energy they have. So this normally wouldn't happen, right? The alpha particle would just be happy rattling around inside the nucleus, having its, extra potential energy from the attractive forces and having its, Q alpha of kinetic energy. So again, when you're far away, there's just purely kinetic energy for the alpha and then zero potential. And here there's negative, 120 MeV potential energy plus this amount of kinetic. So it just doesn't have enough energy to overcome this barrier. Just rattle around in here, being happy with the other nucleons, right? But that is not what happens because of quantum mechanics. And how do we see that? Well, we have to go back to the Schrodinger equation a bit. And I'm only going to be able to do this sort of schematically, but remember Schrodinger equation tells us that the energy of a particle, right, times the wave function is equal to the operator, the Hamiltonian, acting on the wave function. And the Hamiltonian is sort of a combination of the kinetic plus the potential energies. And so here, the potentials are kind of flat, and out here, the potential is essentially zero, far away. So far away, where R is sort of bigger, much bigger than the nucleus radius, where we just have an alpha particle flying out there, radiating out. We just have kinetic energy, which I'm going to do this sort of 1D. So mass of the alpha, h bar squared over 2m. The wave function obeys this equation. Pure kinetic energy. So you have this guy, which is the kinetic energy. And then you have this purely goes into the kinetic energy. There's just this some number. So the value of the kinetic energy, if you wish. So we can rearrange this, and which is also, the total energy. We can rearrange this to look like the following. We have d squared psi dx squared is equal to minus 2m q alpha over h bar squared times psi. This has solutions. This is a differential equation. It has solutions that are sines and cosines. And maybe you remember the Euler formula. You may or may not have seen this, but you can kind of you can combine sines and cosines into a complex exponential using this formula. The e to I imaginary I times theta is equal to cosine theta plus I sine theta. So the solution to this differential equations are sines and cosines, but equivalently, we can write them as what are called plane waves. So the solutions are plane waves. There's a constant, and it's e to the I kx, and another constant, e to the minus I kx. And these kinds of solutions are called plane wave solutions. They correspond to waves. And k is a wave number. It's just equal to, this equation you can also write as is equal to minus k squared psi. It's just, so you have this minus sign, right? When you take two derivatives with respect to x, you'll pull down two factors of I times k, and I squared is -1. So that gives you this minus sign here. And then you get the k squared from the two derivatives. So k is just equal to the square root of 2m q alpha over h bar squared. So you have these plane waves, and what they correspond to, these solutions, are particles moving with a kinetic energy either to the left or to the right. So this is the alpha particle moving in the plus x direction, and this solution corresponds to the alpha particle moving in the minus x direction. So, okay, that's what you have there. For this one over here inside the nucleus, you also have a particle kind of running around. And it's running around with a much larger energy. So, right, the inside the nucleus, so this is sort of far away. And inside you also get sort of plane wave solutions. So inside nucleus, you'll have again minus h bar squared over 2m alpha. You have a minus u for the potential energy, and that has to be equal to the total energy of the alpha particle, which is again just q alpha times psi. So inside you also get these plane wave solutions, but with a different k, right? So you can rearrange this, and this becomes 2m alpha over h bar squared, and you just get q alpha plus u psi. So same kind of equation, except now k is equal to square root of 2m over h bar squared q alpha plus u. Okay, so that's inside and sort of far away from the nucleus. And what happens in this barrier region? So here you have these kinds of plane wave solutions, and here you have these kinds of plane wave solutions. In between, you actually can break up the problem into a series of steps. You can imagine that this barrier is composed of a bunch of rectangular barriers like this. And inside each one of these, you'll have a similar thing going on where your total energy is q alpha. But now, instead of your potential energy being a negative constant, it's going to be a positive constant. So it's going to be plus v here, where v is given by this guy right here, the Coulomb potential energy. And so you'll actually get a different sign in your differential equation. And I'm going to have to leave it there for now, but what we'll do next time is sort of try to see what happens in this barrier region. So basically, what we'll look at, and I'll redraw this potential, we will see that the wave functions, just give you a teaser of what they do in this extra region. So we know here there are plane waves corresponding to particles zooming around, and then here there are plane waves solutions corresponding to particles moving around. And in between, in this region where your potential energy is bigger than your total energy, you actually get exponentially decaying solutions for the wave function. And it should make sense. Remember when we looked at this kind of potential, we looked at one where basically it was the nucleus and then it shot up to infinity. This is for the potential, and this is V. This is what we looked at, a simplification of the nuclear potential. And basically what happens there is that the wave function just vanishes outside of here. But as it turns out, if you make this barrier finite, and your total energy is somewhere here for your particle, then what happens is that your wave function is not just zero anymore outside of here, it just exponentially decays. So the wave function will look like wiggles in here. It's a particle zooming around with some kinetic energy. And then the wave function will decay to zero in here. And because it doesn't decay to zero immediately, if this barrier is finite, if it stops after some time, goes back to zero, say, then what will happen is that the wave function will decay, but not all the way. It'll still be a little bit non-zero probability that the particle makes it out of here, makes it out of this barrier, and it'll start wiggling again out here. So I'll talk a little bit more about that next time, and hopefully finish up this calculation. It's quite beautiful. You can get so many things from it. You will get that. You'll get this dependence, and we'll also get a value for the half-lives. We'll actually be able to determine what the half-life is of alpha decay. So we'll do that, and that'll sort of finish up our more detailed understanding of alpha decay. So thanks.